So now that we've taken a quick look at the data set, let me show you something pretty cool. So let's introduce what's called the GraphLab canvas. So this kind of tabular data, graph data, text data, image data that we have, there's many ways you can visualize it. What we have inside GraphLab Create is a data visualization companion that can be used to view the data in various ways. So if you take any data structure that we play with, any data structure in GraphLab Create, so take any data structure in GraphLab Create, and you type .show after it. So if you type sf.show, it's going to start the GraphLab canvas and give you visualization, first visualization of the data structure. In this case, we have a very simple data set. When I type .show, it gives me a link here to a new web page that shows you that data set. So I'm going to decrease the font size a little bit, and you'll see this data set has 4 columns. The first name, Alex, Malcolm, Felix, and so on. The last name, the country this person lives in, and their age. And you see that the max age is 25, the mean age is 22, the median age is 23, the mean age is 23.143, and so on. If you can click on tabular view, you can actually view the data. And this is pretty cool. If you have a million rows, it's really hard to actually view the data, but this allows you to scroll through millions. 1 billion rows you could scroll through with this tabular view. And now if I click on any column, for example, the age column, is going to give me, sorry, I selected something here, which was a little weird. Let me just type reload because I did something funny. A histogram, but if I type categorical, it's going to sort it by the most common value. You see that the most common value is 23. There's 3 of these folks, and so that's 42% of the data has age of 23. So you should play with, we can play with Canvas and visualize the data in various ways and get started. Now, for the notebooks that we're filming here, the Canvas popping up in a new window like this makes it kind of awkward to go back and forth when we're just filming. So instead of opening as a new window, what I'm going to see is how to open the canvas or some of visualizations inside of the IPython notebook. So I'm going to call a command called graphlab.canvas.setTarget, and I'm going to say that the target is the IPython notebook, short IPyNB. And we're going to do this again, again, again. But what happens is now the visualizations that we do are all going to target this actual notebook. So let's visualize again the age column, but now inside our notebook. So here's what we're going to do. It's pretty cool. We're going to take this S frame SF, and I'm going to select, square brackets allows you to select a particular column or many columns. So I'm going to select the column age, just one, and I'm going to type .show on it, and I'm going to tell it that the view that I want is that sorted categorical view that we just saw. So here we go. We just saw that 23 is the most common age, people with 23 years of age, 42% of the data. So now we've seen how to do a little bit of visualization using GraphLab Create. We're going to see several other visualizations within GraphLab and within other tools during the course. So next, we're going to inspect some columns of our data set. So let's inspect some columns of the data set. So let's take a look at it. So if I type SF of country, what it's going to do is select a column country, and since I don't do anything to it, I don't set it equals to anything, it's just going to print it. Now it says United States, Canada, England, USA, Poland, United States, Switzerland. So that's that whole column, but printed horizontally. Now let's look at another column. So for example, let's look at the column age. So sframe.age, I'm just going to look at it. So you have the column is 24, 23, 22, 23, 23, 22, 25. Same one that we did a visualization up here. Now we can take that same column sf.age and do some computations on it. So if you type .mean, it's not saying that column is mean, you mean column, but actually computing the mean of that column, which the mean age is 23, 14, 28, 57, so on. Now you can compute, for example, the max age. So SF of age and say max, and again you get 25. That's the maximum age. Now this is some pretty cool stuff, but let's do more. Let's create new columns in our S-frame. So when you're doing machine learning, often taking columns and transforming them, creating new ones, this is called feature engineering. We're going to do a bunch of those. I'm going to do now a creation of a new column. So let's go back and print our S-frame. And you see that there's a first name column and there's a last name column. There's no full name column. Let's say that you wanted to create a new full name column. It's pretty easy. I'm going to say SF, or S-frame of full name. So there's going to be a column called full name. And what is that column equal to? Well, it's just a concatenation of first name and last name. And in Python, it's really easy to take strings and concatenate them together. All you have to do is put a plus sign. So we can do SF, S-frame of full name is going to be the first name column. So first name. And then I'm going to put a space between it. So plus a space plus the last name column. So last name. Now this is pretty cool. I just create a new feature, new column called full name, which is just the first name space last name. It's very easy to do these things in Python, especially if you don't have typos. I see that this is fifth name instead of first name. So, and there we go. So now if you go back and show that S-frame again, you'll see there's a new column called full name that's been placed at the end. So Bob Smith is the first full name there. Now you can do all sorts of interesting things. So for example, you could take the age column, and I'm not going to create a new column, but I'm just going to do add 2 here to the age column, and you'll see that it's just going to add 2 to every element. And so you can do these kinds of operations. For example, you can do age and multiply it by the column h again. Now what happens when you do that? H times h, you're going to get h squared in every element, and you get 566, 529, and so on. So that's how we do various transformations with our data. But these are very simple mathematical operations. Let's do an advanced data transformation. So we're going to use what's called the apply function to do a let's call it an advanced transformation of our data. So this is going to be pretty cool. So we're going to use it to define a new function. We're going to do a bunch of things here. So here's what I'm going to do. We're going to look at the column country. Notice that there's a little bug in my data set. Some people's country is United States, and some people's country is USA, and some people's country is United States. So if you're just building a machine learning model, you'll see that they'll think that USA is a different country from the United States, and you want to make sure that it's the same country. So I'm going to take everywhere where it says USA and substitute that with United States. So we get different counts. So right now, for example, if I do SF of country, dot show. So if I just show that, you'll see that United States has 2 counts and USA has 1 count over here. And that's kind of a problematic thing. So let's fix that. So the first thing I'm going to do is create a function that if the input is United States, USA changes to United States. So let's define a function. We talked about how to define a function in Python. I'm going to call it transform country. And it takes into input a country, and you put a column at the end, press enter, and you have to align things vertically. So it says if the country is equal to USA, then we're going to return United States. So this way we normalize the data. Else, so if it's not United States, we don't do anything. So we just return the country as it was. So we created this function transform country. So we can now execute it actually. So let me just show you what happens as an example. So if I compute transform country, give it to input Brazil, it returns Brazil, doesn't do anything. And in fact, if I give it as input Brazil, we say Brazil. And it has with an S, not a Z, also returns Brazil with an S. This doesn't normalize between the English version of Brazil and the Portuguese version of Brazil. But if you give as input transform country USA, you'll see that it returns United States. So it's going to fix that kind of mistake. Now, what I want to do is go line by line in my data set, and whenever I see the word United States in the country column, I want to change that. Sorry, USA in the country column, and change to the United States. So I want to apply this transform country to every row of the data. And you could create a for loop, and that could be kind of annoying. And this is where the apply function comes in. So here's what I'm going to do. I'm going to run a function on the country column. And what apply does, it takes this function transform country that we defined, transform country, and apply it row by row. Let's see what the output would be. So if I run it row by row, it says, it prints some statistics, but it says United States, Canada, England, United States, Poland, United States. So all the USA's changed to United States. And now what I could do is say, I want to take my country column, and I'm going to fix it by saying take what it used to be, the country column, and apply this transformation to every single line and just store it back into the country column. And now if you look at our S frame, you'll see that you have United States, no USA in this column. Great. So we've seen how to create functions, how to transform some columns, how to create new columns with S frames, and how to show our data. Now this tools GraphLab creating an S frame is what we're going to be using throughout this course, and you will see many ways of applying it and using it, and it's going to make it really easy to build some of the intelligent applications that we're building in this first course.
Okay, so in this module, we're going to talk about regression, which is one of the most widely used statistical tools out there. And the idea is really simple. So we have some set of features, and we want to model how our observations that are associated with these features change as we change the values of the features. And we're going to ground our conversation in a case study of trying to predict house values. So here we can imagine that a house has some set of features like what's the size of the house, how many bedrooms does it have, number of bathrooms, and the list goes on and on. And the observation that we have is what's the value of the house or the house sales price. But the tools of regression go much beyond just thinking about doing prediction tasks. So as we're going to see in the classification course, we can use regression tools for classification. So for example, let's say we have an email and we want to classify whether it's spam or not spam. Well, that email We can think of having features about the text of the email that's indicative of whether that email's spam or not spam. And in addition, we can think about using regression for analyzing the importance of the features themselves. And we're going to talk more about that in the regression course. Okay, so let's talk about this problem of predicting the value of a house. So this is a very important problem. At least in the United States, it's estimated that household wealth is nearly 50% invested in real estate. So this is clearly important both to consumers, individuals, as well as policymakers. Okay, so I'm here, I want to sell my house. I have this nice big lime green house. But I don't know how much to list it for. So I'm not sure what value my house has. And so how do I think about estimating the value of the house? Well, it might make sense that what I do is I look at other recent sales that have occurred in my neighborhood. So I look locally at the region around me and I say, how much have the other houses sold for and what do those houses look like? So what I'm going to do is I'm going to record for each one of these recent sales, what was the sales price and also what was the size of the house that was sold. I'm going to say that that's what signifies whether that house is similar to mine or not. Okay, so being a statistician, I'm going to take all these observations I had and I'm going to make a plot of them. So in the US, at least, the size of the house is measured in the by square feet. So that's going to be my x-axis. And then my y-axis is going to be the sales price of the house. Okay, so that's my y variable. And each one of these points represents some individual house sale. So here, this is one previous house sale in my neighborhood. And just to introduce a little bit of terminology here, when we're talking about regression, people often refer to x, this variable x, as being the feature. That's the terminology we've been using. People also talk about it being the covariate or the predictor. And in some cases, it's called the independent variable. And then our observation y is, as I just said, I tend to refer to it as an observation. People also call it a response or the dependent variable. Okay, so the question is, how am I going to use these observations to estimate my house value? Well, I might look at how big my house is and look for other sales of houses of that size. Well, most likely there are going to be exactly 0 house sales of other houses that had exactly the same square footage as my house. Okay, so I say, well, I can't use this approach. I'm going to be a little bit more flexible and I'm going to look at some neighborhood, not geographic neighborhood, some little range of square footage around my actual square footage here. So I'm going to say, okay, let's look at all house sales that were for houses within this range of square footage. But even with that approach, in this case, for example, I only have 2 house sales that I'm going to base my estimate off of. So I don't really feel very comfortable with that. And what I'm actually doing here is I'm throwing out all these other observations as if they had nothing to do with the value of my house. And the question is that reasonable? Do we actually believe that there's actually no information in these other observations? Well, when I look at this data and when I think about data, I like to leverage all the information that I can to come up with good predictions. Okay, well, instead of the analysis that we just did, we can instead think about modeling the relationship between the square footage of the house and the house sales price. And to do this, we're going to use something that's called linear regression. Okay, so to leverage all the observations that we've collected, what we want to do is be able to understand the relationship between the square foot of the house and the house sales price. And so the simplest model we can use for this is just fitting a line through the data. So here's an example of a line fit to this data. And this line is defined by an intercept, W0, and a slope, W1. And so often we'll talk about W1 being the weight on the feature X, or it's called the regression coefficient. And what this weight has an interpretation of is as we vary x, the square footage of the house, how much of an impact does that have on changes in the observed house sales price? Okay, so these two things, our intercept and our slope, are the parameters of our model. And so to be very explicit here, we're going to write this function, this linear function here, with a subscript w that indicates that this function is specified by parameters w, being the set of w0 and w1. Okay, so this is the line that we fit through the data, but a question is, which line is this, the right line or a good line to use for a given data set? So maybe we could draw this line or this one instead, and each one of those is given by a different set of parameters w. And the question is, which w do we want to choose for our model? Okay, well, to think about this, let's talk about defining a cost for a given line. And one very common cost associated with a specific fit to the data is something called the residual sum of squares. So the residual sum of squares, we take our fitted line and we look at each of our observations and we look at how far is that observation from what the model would predict, which is just the point on the line. So we look at all of these distances here, and we actually look at the square of these distances. That's why it's called the residual. The residual is the difference of your prediction and your actual observation, and we're going to look at the square and we're going to sum over them. Okay, so this is the equation here more explicitly, where we have the price. This is our observed house sales price for the first house. And what is this term here? So if this is what I'm calling dollar house 1, then what this point here is if this is square footage of house 1, then this x that I've drawn here represents exactly this term here. This is that value, the point on the line. So this dollar sign minus this term here is the difference between our observed house price versus what our model, just this line, predicts for this given house square foot. And we're squaring that, and then we're summing over all the different houses in our data set. Okay, so when we think about trying to find the best line according to this metric that I've defined here, this residual sum of squares, what we do is we search over all possible W0 and W1, so all possible lines, and we choose the one that minimizes this residual sum of squares. So we're going to denote the resulting W as W hat. So remember, that's going to be the set of W hat 0 and W hat 1, our intercept and our slope. Okay, so there exists really nice and efficient algorithms for computing this W hat, this search over all possible W's we could look at, parameters of this model. But we're going to discuss these algorithms more in the regression course. Okay, so now let's talk about how to take our estimated model parameters and use them to predict the value of my house. So I've gone through, sorry, this star shouldn't be there. This should be a hat, just to be clear. And I've gone through and plotted the line associated with our estimated W0 hat and W1 hat. And now here's my house. This is its square footage. And the best guess of my house price is simply what the line predicts. So I go and I compute what is the value for this square footage of my house, which is W0 hat plus W1 hat times the square footage of my house. Okay, very, very straightforward. Okay, so up to this point, we've just considered fitting the data with a line. And the question is, was that a good choice? So I'm actually feeling pretty good about my analysis, to be pretty truthful here. I fit this line, I minimized the residual sum of squares, I made a prediction for my house value, and in doing so, I leveraged all of these observations that I went through and recorded of all the recent house sales. And I go to Carlos and I say, hey, look at my analysis. This is my estimate of the value of our house. And he goes, well, I'm not so sure, because really to me, I'm not sure that this is a linear trend. He actually says it's not linear. Or according to my cartoon, he says, dude, that's not a linear relationship. Dude. No, I guess Carlos would not say dude, but anyway. Bro. He says bro. Okay. Bro. He always refers to me as bro, of course. Okay, but anyway, the point is, Carlos doesn't think that it's a linear relationship. He thinks, maybe it's quadratic. He said, did you try a quadratic fit? I go, well, no. I look at the plot that he just put up here and I say, actually, that looks pretty good. And what do I have to do? I have to figure out which is the best quadratic fit to this data. And how am I going to do that? Well, I'm going to go again and I'm going to minimize my residual sum of squares. So I'm just about to go minimize my residual sum of squares. So let's talk about what that would involve. Because when I'm looking at a quadratic function, I now have 3 parameters here. I have my intercept, which is just where is this curve up and down on the y-axis. And then I have this linear term of x. And then I also have this extra term here, which is now the square of x. That's where I get that quadratic component. But I want to make one quick comment here, so a little aside, that this is actually still called linear regression. And the reason is because we think of x squared just as another feature. And what we see is that the w's always appear just as w's, not w squared or other functions of w. And we're going to discuss this in more detail in the regression course. But remember, even though we're talking about a quadratic function fit to the data, this is still called linear regression. Okay, but the point I want to make here is we have 3 parameters. So when I'm going to minimize my residual sum of squares, I have to search over the space of 3 different things now. I have to minimize over the combination of best W0, W1, and W2 in finding the quadratic fit that minimizes my residual sum of squares. Okay, so I'm just about to go and do this computation, which actually turns out to also be efficient. And again, we're going to discuss the generality of that in the regression course. But then Carlos has a brilliant idea. He says, wait. I told you about that quadratic, but did you try a 13th order polynomial? And I go, no, I didn't.
Makes sense.
It does. It makes a lot of sense. Look at this. This is pretty good. This is the fit that Carlos gets with his 13th order polynomial. He says, I just minimize your residual sum of squares. Pretty good, right? My residual sum of squares here are basically 0. But I'm personally not feeling so great about this because I'm looking and I'm saying, my house isn't worth so little. I know that. I do. Yes, we talked about residual sum of squares as being this cost of the fit. And yes, Carlos seems to have really minimized my residual sum of squares, but something's not sitting right with me. This function just looks crazy. In this module, we've seen how regression can be used to predict house prices and also be useful in a wide range of other applications. So in the introduction to this course, Carlos introduced this machine learning pipeline where we go from data, which gets shoved into some machine learning method, and we use that to derive intelligence. Well, let's dig into this block diagram and expand it now that we've seen some of these machine learning tools in a little bit more detail. Okay, so now we know that what we actually use to fit our data is some training data set. So that's going to be our data, and in our housing application, where we're going to predict the price of some house, the data that we collected was we had this table of the house ID and some set of house attributes, as well as that house, the house's sales price. And we had this for a whole bunch of houses in our neighborhood, and we collected this data into some table. So that represented our training data set. And then we took that data, and what we did was shoved it through some feature extractor, which in this case is a very simple feature extractor, where we just choose some subset of the house attributes. So in the examples we looked at, X, our set of features, represented things like we looked at square feet of the house, and we also looked at number of bathrooms, and we talked about possibly using more features. Again, we'll talk about that more in the regression course, but those were two that we examined in this module. And so then what did we do with these features? Well, our goal was to take these features and have some type of model that led to a prediction of the house price. Okay, so our output, the intelligence that we're deriving, is the predicted house price. And we're going to do this for every house in our training data set. We're going to take its associated features and shove it through this machine learning model and predict the house price. And what's the machine learning model we talked about? Well, in this case, it's regression. That's our specific machine learning model that we're looking at here. Okay, but remember that this machine learning model had some set of parameters. Okay, so the parameters we call W, these are the weights on our features. So for example, it's the weight on square feet or number of bathrooms and so on. More technically, these are called regression coefficients. And we talked about estimating these parameters from data. So that's our W hat is our estimate of these parameters. And how did we talk about doing that? Well, we took our predicted output, so our predicted house price, and we compared it to the true house price. So the actual sales price that we recorded in our training data table. So Y here is our actual sales price for the houses in our training data. And we compare to the predicted house price, and we use a quality metric to measure how well we're doing with our prediction, using our model, using W hat as the parameters of that model. Well, how well are we doing? What was the error metric we talked about? The error metric we talked about was something called residual sum of squares, where we just sum up the square difference between the actual house sales price and the predicted house sales price, summing over all houses in our training data set. Okay, so our quality metric is going to take our predictions and our actual house sales observations, spit out this error, and it's going to go into a machine learning algorithm that's going to be used to update the weights, update our parameters of our model. And we're going to talk about this machine learning algorithm or different variants of it a lot more in the actual course on regression. But this is the overall flow chart for this machine learning method for our house prediction problem. And this loop here, where we're taking our predictions, computing our error relative to the actual house sales prices, and updating the weights or our model parameters, this process tends to happen in an iterative way where we update values again and again. Okay, so if we abstract away, what we see is we have some training data set, we have some feature extraction process, we have some machine learning model, and it's going to produce some intelligence, which in this case is a prediction. And we're going to assess the quality of our intelligence with some quality measure, and we're going to use that error or accuracy, depending which way we're thinking about measuring it, to adjust our model parameters using some algorithm. And we're going to see this type of flow for machine learning again and again. In this module, we've seen how to take our data and derive intelligence using something called regression, where we have a model that relates our features to our output. And we talked about this in the context of predicting house values. And you also work through a really interesting IPython notebook. And from this, you should be able to deploy really interesting regression models in practice now.
In this module, we talked about how to do regression. In fact, we talked about how to use it to predict house prices. Now we're going to build together an IPython notebook using Python to predict house prices for a real data set based on what's called King County data. King County is the county or the region where the city of Seattle, where Emily and I live, is located. So we're going to take some of that data, it's public record data, and actually build together a regression notebook to predict house prices. So let's get started. Okay, so here's a blank IPython notebook. And just to start, what I'm going to do is hide the... Oh, first let's change the title. So we're going to change the title to Predicting House Prices. So we just renamed it. And I like to go to the View menu and hide the header and hide the toolbar, this part at the bottom, so we have more space on the slide. So we've done that hiding. And the first thing we're going to do is fire up GraphLab Create, the tool that we're going to use to run some machine learning algorithms in Python. So I'm going to type scam, and I'm going to say fire up GraphLab Create. So we do that by typing import GraphLab. And that just starts up GraphLab Create. Now, our task today is to predict house prices. So the first thing that we're going to do is to load some house sales data. So this is public data, public record of houses that got sold in the Seattle region. So I'm going to call this table data sales, and I'm going to say graphlab.sFrame. Remember we talked about sFrame as the data structure for representing tabular data in GraphLab Create. So it's a really fast, out-of-core data structure, and we're going to load up some house listings in there. So this is going to be called home underscore data. And notice that IPython notebook does autocomplete for you. So that just happened there. And so if I just type, this is loading it up and it's firing up GraphLab Create. If I just type sales here, you'll see what that data looks like. So I'm going to scroll up a little bit to the top. I just type sales and it says there was an ID for a date for the sale, the price, number of bedrooms, number of bathrooms, square feet, which is kind of like the American version of square meters if you're living in other countries, for the house, square feet for the lot of land, number of floors, and a bunch of other categories, whether the house has a view or not, whether it sits on a grade, which means it's on a hill, and a bunch of other measurements. So we've loaded this house data and it looks pretty cool. The first thing that we're going to do is use GraphLab Canvas to do a little bit of visualization. So what I'm going to do is, again, create a cell, and this says exploring the data for housing. So housing sales. So we're going to do some data exploration. So we're going to take the sales data and I'm going to show. So when I type .show, it's going to show some visualization of that data. And in particular, what I'm going to do is view, just rather than letting GraphLab create this default view, we're going to just do a scatter plot. So we'll see what a scatter plot is in a second, but just type view scatter plot that relates two variables. On the x-axis, we're going to have the square feet of living space, and in the y-axis, we're going to put the price. So what that should show us is the relationship between square feet of living space and price. Now, one little trick that I like to do when I create notebooks is that sometimes we push out GraphLab Canvas in a new tab, but often it's kind of fun to just plot those scatter plots and simpler plots inside the notebook itself. So I can print it out and hand it off to somebody. So the way to do that is I can just tell GraphLab Canvas to set its target not to be the browser, which is the default target, but to be the IPython notebook. I just type canvas.setTarget IPyNB, IPython notebook, and it's going to plot this scatter plot on the canvas, on the notebook itself. So if I hit enter here, what's going to do is take those two axes and just plot them together. So here we go. On the x-axis is the square feet of the house, and the y-axis is the price. So let's kind of browse this a little bit. So for example, more square feet are big houses. So if I mouse over here, you'll see that this big house had 5,990 square feet, which is pretty big. That's like 600 square meters. And it was sold for $2.2 million, which is quite a lot of money. Now, you also notice there's a nice relationship that bigger houses tend to cost more. There's a big blob of houses here, so most houses are between 1,000 and 3,000 square feet. And even at this level, say this house over here, it's an outlier. So even though it's only 1,910 square feet, it was sold for $1.5 million. While down here, there's a house that is similar, 1,700 square feet, that's sold for just $149,000. So it's a big discrepancy. And here's the biggest outlier of this data set. This house has 3,730 square feet and got sold for $2.5 million. So we've now built a simple scatter plot, and we get an idea of what our data looks like. And the question is, can we use the scatter plot to predict sales price from square feet of living? So we're going to do a simple regression model. So let's do that. I'm going to hit askm, and we're going to say create a simple regression model of square foot of living to price. All right, so let's do just that. So remember from the lectures that the first thing that you do before you do anything to your data is to split it into a training set and a test set, because you never want to do training or learning on the test data. You want to do that just on the training data. So let's do that, split. So I'm going to take my data and split it into training data and test data by calling a function that's called, that you can apply to an S-frame. So it's called the random split function, sales.randomSplit. By the way, what I did there was just use tab complete. So let me just show you that little trick just for a second. So if I just do sales.r and I press tab, you'll see there's a few things I could do: random split, read a CSV file, remove columns, rename columns, and so on. So I'm going to just do random split. And what I'm going to tell it is to do a 0.8 split. So 0.8 of the data, 80% is going to be for training and 20% is going to be for testing. Now, one last thing that will be useful for your homeworks and in general to make sure that you have always the same results is to set a seed for the split. Because it's a random split, it's a pseudo random number generator, we can set a seed to it. And I'm just going to set the seed to be any number we want. For example, it could be 2015, it could be many things. So I'm just going to set it to 0. So now every time I do this random split, it'll split the data in the same way. So now we have some training data and some test data. And what we can do next is build So I'm gonna do as a subheader here, build the regression model. So GraphLab Create has many algorithms pre-implemented for various machine learning tasks, or you can implement your own if you like. And during the sequence of the specialization, you're going to write many algorithms of your own. But for this course, we're just going to use pre-implemented algorithms so you can really try to understand how machine learning works. So what you can do with machine learning. So what we're going to do is build a square foot prediction model, just call it square foot model. And in GraphLab, there's something called linear regression. So linear regression is what we learned, what we explored and talked about and really understood quite well during the module that Emily was teaching. And so if you just say linear regression.create, it's going to create a linear regression model for you. And .create is the name of the project here, GraphLab Create, and create is also the verb that you use to create various things with GraphLab Create. So we're now going to create a linear regression model, and what do I have to give it as input? I give it the training data. So here's the training data. You have to say what variable you're trying to predict. So that's the target. So I'm going to say the target is going to be price. So I'm trying to predict price. And the question is, what are the features? What is the input? So I'm going to say that the features, and by the way, you can use tab complete even within parameters of functions, which is pretty cool. So the features is a list of features. If you don't give anything, it will use all features, all columns of the data. But here, the only feature input we want to use is a square feet of living space. And that is a string that I need to put in. So I forgot to put it in quotes. So let me fix that real quick here. So open quotes, close quotes. All right, very good. So let me just reread that for us. So square feet model, GraphLab, linear regression.create on the training data to predict the target price using features square foot of living. And let's go and execute this. Oh, training data, I wrote data twice here. You see the error came out here, training data underscore data. So now let's execute. So what's happening here? It's done actually, but what we did was create a linear regression model. It used a particular algorithm called Newton's method, but GraphLab Create chooses an algorithm automatically for you unless you tell it which one to use. And this algorithm allows you to make some predictions on the data. We've learned, now together we learned two regression models from our data, one just based on square foot of living, the other one based on this more advanced features. So let's apply these models. Let's see what it looks like when we use them in practice to predict house prices. So what we're going to do is apply these learned models to predict prices of 3 houses from the data set. So 3 different houses. So the first house is, and this is 3 that I picked that had kind of different sizes, different properties. They look a bit different in different neighborhoods. So let's just look at them. So the first house is from our data, and so what we're going to do with this house is, so this is from not data, but sales data. So out of my sales data, I'm going to select the house whose ID is equal to a particular ID. And so the county record gives this string IDs for every house. It gives it a number. So this one is 5309. I'm copying from a piece of paper here. 101 200. So a particular house for a particular ID. And so I'm selecting it. And if I type house 1, you'll see what it is. So it's the house that has this particular ID. It got sold on this date for $620,000. Had 4 bedrooms, 2.25 bathrooms, 2,400 square feet of living space, and so on. Now, what you can do is, in IPython Notebook, you can embed not only markups and text and Python code, but you can also embed HTML and images. So let me just do that for you right now, just as an example. So I'm typing XM, and I'm going to add an image to my notebook. And this image is an image that I downloaded from the county records for this particular house. So the image is on my directory. It's called house. So house 53, what was the number? 09 101 200. So this is going to be pretty cool. I'm going to see a picture of the house we're trying to make a prediction for. Oops, I must have typed that wrong. Oh yeah, I forgot, it's .jpeg. And that's pretty cool. Here's a picture of the house we're pricing. So this house was sold in 2014 for $620,000. It has 4 bedrooms, 2.25 bathrooms, and it was built, for example, in 1929. Now, let's see what our model predicts. So we had 2 models. So we had first, so the true price of the house. Let me just print that to remind ourselves. So this is house 1 of price. This is 200. So if I just type print here, it'll look a little nicer. $620,000. This is the house price. Then let's see what my first model predicts. So that was the simple square foot model that we built. When you give it, so I'm going to type .predict to predict the price of house 1. And it says it predicts it as $628,000. So pretty close, actually. That's really good. And let's see what adding more features did for us. My features model dot predict house 1. So you remember, on average, the my features model, with adding more features, give you better performance. Now, if you look at the prediction here, it's $720,000. So the square foot model had a better prediction than the one with more features. So what we learned here is, even though on average, adding more features give a better prediction, for this one particular house, the simple model did a better job than the more advanced model. But this is to be expected. Not always, but sometimes it's going to do better, sometimes it's going to work, but on average, it's going to do better. So we've seen this one example, and now let's look at a second house. So I'm going to now prediction for a second fancier house. So let's look at that. So let's call this house 2. So house 2 from our sales data, is going to be the one, again, we're going to use a filter here. So it's the one whose ID is equal to 1925069082. So let's take a look at what house 2 looks like. House 2 was sold in 2015 for $2.2 million. It has 5 bedrooms, 4.25 bathrooms, so many more bathrooms, 4,640 square feet of living space, so it's much bigger. It's about 460 square meters. It's a pretty big house. So let's look at an image. I kind of downloaded also an image for this house. So here's my little cheat sheet for the image. And I'm going to insert it. So SCAM. So as before, we're going to do an image whose source. So this is I downloaded to the basic directory here. It's called house 1925069082.jpg. Close, not jog, but JPEG. So that should work. So remember that other house cost $620,000. This one costs $2.2 million. Let's take a look at it. It looks fancier, it looks cool, it has a bigger yard, but check this out. It's on the water. It's a waterfront house. You know, that explains why it costs $2 million. It's fancier, much fancier. So let's see now what our models predict for the value of this property. So it costs $2.2 million. Let's print what the square foot model predicts. So just like before, we're going to do dot predict on house 2, and it predicts it costs only $1.25 million. So it didn't do so well. So let's look at what the more advanced model, so my features model dot predict does. And before I hit enter here, it's good to start thinking about what should happen here. The other house, the one above, where the one with more features, model with more features didn't make a big difference or actually did worse, was a pretty standard house for Seattle. Standard number of bedrooms, standard number of bathrooms. It was kind of common, so you expected both models to do about the same. But this house is crazy. It has features which are hard to capture just because of the square feet. It has waterfront, it has lots of bathrooms, lots of bedrooms. So we expect here for the more advanced feature model to do better. Oh, I misspelled something. Oh, I forgot. Here my features model. Sorry about that. That was a little anticlimactic. But if we run it, you see it's 1.38 million. It's a little closer. As you remember from before, the error difference wasn't too big, but here it's a little closer to the true price. So it does a bit better on this house. Now, just to conclude, let's do a even fancier house. So what I'm going to look at, so a third house. So the last house is going to be super fancy. Fancy. And in fact, what we're going to do is take Bill Gates' house. Bill Gates lives in the Seattle area, and try to predict what the house looks like. So it has a lot of different properties, and rather than typing them all in, I'm going to paste them in. So I'm going to paste it here. And this is what Bill Gates' house would have if it were in the data set. It has 8 bedrooms, 25 bathrooms. Bill Gates, you really need to go to the bathroom, apparently. 25 bathrooms, at least that's what I saw online. It has 50,000 square feet of housing. That's about 5,000 square meters. It's a big house. 4 floors, lots of stuff. So that's what his house looks like. We actually don't know what the house is worth because it's never been sold. I guess he doesn't need the money. But here it is. And let's see what that house actually looks like. So, I actually have a little cheat sheet here with a link to an image of his house. So this is a picture of Bill Gates' house. And here we go. Oh, yes. Sorry about that. I forgot. I had to tell it was a markup. And there we go. So let's see what the model predicts for the price of Bill Gates' house. So I'm going to print what my features model dot predict says for Bill Gates' house. Now, these are GraphLab create models, and they only take S-frames as input. So I have to take that dictionary that I just created to describe Bill Gates' house and convert it to an S-frame. So I just type graphlab.sframe of Bill Gates. This was a dictionary, which is what we defined above here. That's called a dictionary. And I convert it to an S-frame, and I execute. And it says it predicts it to be valued at $13 million. I don't know. Sounds like a lot, but the house might be worth a lot more than 13 million. Who knows? And that was exciting. We built 2 models of house prices using county data. We explored it, we used it, and we applied it to this task of predicting houses. We even found out what we think Bill Gates' house might actually be valued at. Today we're going to talk about classification, which is perhaps one of the most common areas of machine learning, one of the most used and useful areas of machine learning, and perhaps one of those most intuitive ones as well. So things like figuring out whether your email is spam or not, or whether a document comes from a sports topic, or it's about politics, or it's about entertainment, and so on. But as usual, we're going to start with a use case, which is an exciting one around restaurant reviews. There are many systems for restaurant reviews out there, but today we're going to talk about a pretty new and exciting one that we can build. So it's a new, it's an important day for us, and we're trying to book a Japanese restaurant. And we love Japanese food and want a really cool place to have some Japanese food. But this is Seattle that we live in, and Seattle is really awesome for Japanese food. So there are many, many places for sushi, and in fact there are many that have really good ratings, say 4 stars. So perhaps when I'm thinking about a restaurant to go to, I'm not just thinking about the overall stars of the restaurant, but I'm thinking about how is it in terms of the food, in terms of the ambience, in particular, how is it in terms of the sushi, which is the thing that I really care about. I really love sushi. I want really the best, the freshest fish, and the most awesome, innovative sushi I can get. So when you talk about a positive review for a restaurant, and here's a restaurant that we love in Seattle, a sample review might go something like this. So watching the chefs create an incredible, edible piece of art was really a unique experience. So the experience is really positive, if you think about that aspect of the restaurant. But the review might go on to say, well, my wife tried the ramen and it was pretty forgettable. That means the ramen, not so good. Now, the review continues and says, oh, the sushi was delicious. Easily the best sushi in Seattle. So the sushi was really 2 thumbs up. Now, I don't care about the ramen. I'm not going to this place for ramen. I don't care that this person really didn't like the ramen or his wife didn't like the ramen. What I really care about is good experience and amazing sushi. So this review is just for me. So when I'm thinking about restaurant reviews, I want to understand the aspects of the restaurant that are positive or negative, and really think about which ones of those really affect my interests. So if I look at all the restaurant reviews, I'm going to feed them to this new, really exciting new type of restaurant recommendation system that's going to tell me the experience was good, 4 stars. The ramen was so-so, but who cares? But the sushi, the thing that I really care about, that was 5 stars. And not just that, it's going to give me some interesting feedback. So for example, this is easily the best sushi in Seattle. Now that's where I want to go. So how do we build such an intelligent restaurant review system? Well, we're going to start with all of the reviews, and we're going to break them up into sentences. So each review is composed of multiple sentences, and some sentences cover different aspects of the restaurant. So for example, a sentence that says, easily the best sushi in Seattle. I'm going to feed that sentence through a sentiment classifier. So sentiment classifier is going to say, is this sentence positive or is it a negative sentence? Now we have a sentiment classifier, which can take a sentence and say, is it positive or negative? So how do we build this new kind of cool restaurant review experience? So we're going to take all the reviews and break them into sentences as we discussed, but then I'm going to select the sentences that talk about the aspect I care about. So which ones of these are really about sushi? So not all of them, but a subset of those. Then I feed those sentences through the sentiment classifier, each one of them, and then I average the results. So in this case, all of the sentences were positive, and so I'm going to say this is a 5-star restaurant review in terms of the sushi. And not just that, I can look at the sentences about sushi and look at which ones are most positive. So for example, this one might be the positive, but easily the best restaurant in Seattle, maybe it's the most positive, and I can display those. I can also display the most negative ones. In this case, there's nothing negative to say about the sushi. So we now built a whole new kind of restaurant experience restaurant review experience using classifiers. So let's dig in and really understand a little bit more what a classifier is and some other applications of classification. So a classifier takes some input X, for example, a sentence from the review or other inputs as we'll see. It pushes it through what's called a model to output some value Y that we're trying to predict. And here it's a class, for example, positive or negative. So positive in the case of sentiment analysis corresponds to thumbs up reviews, while negative corresponds to thumbs down. But this is just one example of classification. You can look at text, for example, a web page. I want to figure out which web pages interest me, and I can align them to categories. For example, is this about education, a page about education, is it a page about finance, is it a page about technology, and so on. So there's not just 2 categories, there can be 3, 4, or even thousands of categories I'm predicting from. Now, another example of classification, which really has impacted all of our lives, is in spam filtering. Some of you might remember, perhaps in the early 2000s, what spam filters were like. The quality was not very good. Really, they were all hand-tuned things where somebody said, oh, if it has certain words, it must be spam. But the spammers kept changing the words a little bit, adding numbers instead of letters and beating the spam filters. And what really changed the world of spam filtering, it changed it so much that I don't even look at my spam folder. Actually, sorry if your message went to my spam folder, just don't open it. Is machine learning. It's classifiers. They took the input X of the email and they fed it through a classifier that predicted whether it's spam or not, and did that really well. And it does it by not just looking at the text of the email, but it looks at other characteristics. So for example, who sent it? If it's somebody who's a close friend or somebody I have lots of communication with, it's less likely to be spam. The IP address, does that person send it for their usual computer, and so on. Lots of information. So this is another really interesting prototypical application. In computer vision, we do a lot of classification. We're going to take an image and figure out what is in that image. So for example, here, the input X are the pixels of the image. We feed it to a classifier and we're going to predict things like, is this a dog? In fact, it's a Labrador Retriever, Golden Retriever, or a different kind of dog. This is actually my dog, Labrador Retriever. And as we'll see later on in the deep learning module, there's really interesting new ways of doing this with very high accuracy. Now, you can also use classification in medical diagnosis systems. And in fact, this is what your doctor does. They take your temperature, maybe they look at your x-ray, they look at some medical tests, and they try to make a prediction about what's ailing somebody. Maybe they say, no, you're just healthy, or you have a cold, you have the flu, maybe you even have pneumonia. That's a variable Y that's being predicted. What is the disease that's going on? Now, these days, there's really interesting new things around personalized medicine, because the prediction doesn't just depend on the standard measurements, but can be really personalized to me. Can depend on my particular DNA sequencing, which is pretty exciting, and also my lifestyle. So maybe it looks something like that feature on the bottom left, or maybe a more realistic something like this. And so, given all these measurements, we can make an even better prediction at what's ailing me. Now, this idea of classification and of machine learning has really gone much further, even to be able to read your mind. So when I was at Carnegie Mellon, Tom Mitchell, one of my friends and colleagues at his office next door, and he'd come to me and say, we've done this amazing thing. We can take an image of your brain using a technology called fMRI, which is brain scan, and predict when you're reading a word with text, where you're reading the word hammer or the word house. And so it's really reading your mind. But in fact, he went on to do many really interesting things. So for example, if you're looking at a picture of a hammer or a house, but you trained the classifier only on you reading words hammers and house, he was still able to read your mind and figure out what picture you're looking at. So this is yet the next frontier of classification to understand how the brain works. One of the most common types of classifiers is the so-called linear classifier. So let's talk a little bit about that. The question here is how do we represent a classifier? So we start with some sentences. For example, in a sentiment analysis case, we feed it through the classifier, you get a prediction whether it's a positive sentence or a negative sentence. So how does this classifier work? In the sentiment analysis, we can imagine a very simple kind of threshold classifier. Suppose that I take a sentence and somebody tells me, these are all the positive words, great, awesome, good, amazing, and so on. And here's a bunch of negative words, bad, terrible, disgusting, food, and so on. And so what I can do is take the sentence and count how many positive words there are in the sentence and how many negative words there are in the sentence. Just count those. And then say, if the number of positive words is higher than the number of negative words, then we have a positive sentence. But if it uses more negative words, then you have a negative sentence. So for example, if the input sentence that we have is the sushi was great, positive 1, the food was awesome, positive 2, but the service was terrible, negative 1, you have 2 positives, 1 negative, and in the end, positive wins, and so you have a positive prediction. Now, threshold classifiers have some limitations. Where does this list of positive and negative words actually come from? It has to magically come from somewhere. And not just that, words have different degrees of positive and negativeness. So great is more positive than good. Do you want to tune and figure out what's better, great, good, amazing? Is amazing better than great? Who knows? So how do we figure that out? How do we weigh different words? And single words might not be enough to make good classifications. So good food, so the food was good, is positive. The food was not good, is actually negative. And so these are all issues that need to be addressed. The first 2 areas where the positive and negative words come from and how do you weigh them comes from learning a classifier, and we're going to talk about next. The issue of good versus not good is addressed by using more complicated features than single words, and we're going to talk about it towards the end of the module. So a linear classifier, instead of having a list of positive and negative words, actually takes all the words and adds weights to them. So for example, good might have a weight of 1, great might have a weight of 1.5, awesome might have a really big weight of 2.7, while bad might have a weight of negative 1, terrible might have a negative 2.1, awful might be minus 3.3, because awful is really just awful. And there's words that really don't matter to the sentiment. So things like the, we, where, restaurant, they appear both in positive and negative sentences, so they get weight 0. Suppose somebody magically told you what the weight of each word were. We're going to talk about it in a little bit, how those get learned by the classifier. But given those weights, how do we figure out if the sentence is positive or negative? Here we use the idea of scoring. So for example, take the sentence. The sushi was great, the food was awesome, but the service was terrible. Let's score that sentence. So we're going to compute the score of the input sentence X. So in this case, you get from great, you get positive 1.2. From awesome, you get another 1.7. But from terrible, you get a minus 2.1. right here. And so the grand total here is 2.9 minus 2.1, which is 0.8. And the key here is that since the score of the sentence is greater than 0, we're going to predict that it's a positive sentence. If the score were the opposite, if the score of x were less than 0, then we'd have predicted it's a negative sentence. So this is how a linear classifier works if you know the weights of each word. And this is called a linear classifier because the output is basically the weighted sum of the inputs. Just weight what features appear, what words appear in the input. So we're working with a simple linear classifier to start out with. So in summary, given a sentence and given the weights for that sentence, what we do is compute the score, which is the weighted count of the words that appear in the sentence. And then we say, if the score is greater than 0, we predict y hat to be positive, while if the score is less than 0, we predict it to be negative. And that is a linear classifier. So classifiers are really trying to make decisions as to whether a sentence is positive or negative, or whether a set of lab tests plus x-rays plus measurements lead to a certain disease like flu or cold. That's a decision that needs to be made. So let's talk a little bit about how classifiers, especially linear classifiers, make decisions. To understand decision boundaries, suppose you only had two words with non-zero weight. You have awesome with positive weight of 1 and awful, which is just awful, so it has a negative weight of 1.5. If you have this situation, then the score is going to be 1 times the number of awesomes in the sentence minus 1.5 times the number of awfuls. So we can plot this on an axis. There's the awesome axis, and then there's the awful axis. So for example, the sentence, the sushi was awesome, the food was awesome, but the service was awful. Then that has 2 awesomes and 1 awful. It's plotted in the point 2,1 on the axis. And similarly, for something that has, say, 3 awfuls and 1 awesome, for something that's all awesome, so 3 awesomes is at the point 3,0, and so on for other sentences. Now, let's understand a little better how we score the sentences and what does that imply about our decisions. So, for example, take the point 3,0. That has 3 awesomes, no awfuls. 3 awesomes gives you a positive prediction because the score is greater than 0. And that is true for every point really on the bottom right of the axis. While the points on the top left all have score less than 0, so for example, the point 3 awfuls, 1 awesome is got score less than 0, so those get labeled negatively. And in fact, what separates the negative predictions from the positive predictions is the line that defines the places where I don't know what's positive and what's negative, and that's the line where 1 times awesomes minus 1.5 times awfuls equals to 0. And that's the line where I don't know, the prediction is uncertain, and so we call that the decision boundary. Everything on one side we predict as positive, everything on the other we predict as negative. Now notice that that decision boundary, 1 times awesome minus 1.5 times awful equal to 0 is a line. And so that's why it's called a linear classifier. It's a linear decision boundary. So decision boundaries are what separate the positive predictions from the negative predictions. So in the case of just 2 features, we see this is just a line. But that situation will differ as we increase the number of features. So in 2 dimensions, a linear function is a line. In 3 dimensions, we have 3 words, for example, that have non-zero weight, everything else has 0 weight, then what you get is a plane. And so it's a little hard to draw in 3D, but the positive predictions here are above the plane, and the negative predictions here are below the plane. And the plane is somehow inclined in the space. Now, when you have not just 3 non-zero words, but in real applications, you're going to have tens of thousands of words with non-zero weights. And in that case, we call those hyperplanes, those really high-dimensional separators, called hyperplanes. Now, of course, you can use more than linear classifiers, you can use more complex classifiers. And those, still having lines or hyperplanes, they have more complicated shapes or squiggly separations. And we're going to learn more about that in the classification course. In the regression model, we talked about predicting house prices and fitting a regression model for that. And we measure the error in terms of sum squared errors. Here in classification, our errors are a little different because we're talking about what inputs we get correct and which inputs we get wrong. So let's talk a little bit about measuring error in classification. So when I learn a classifier, I'm given a set of input data. So these are sentences that have been marked as, say, positive or negative sentiment. And as in regression, we split it into a training set and a test set. I feed the training set to the classifier I'm trying to learn, and that algorithm is actually going to learn the weights for words. So for example, it's going to learn that good has weight 1.0, awesome 1.7, bad minus 1.0, and awful minus 3.3. And then these weights are going to be used to score every element of the test set and evaluate how good we're doing in terms of classification. So let's talk about what that evaluation looks like. Let's discuss how we measure error, in fact classification error, when we're doing this classification. So we're giving a set of test examples of the form sushi was great is a positive sentence, and we're trying to figure out how many of these test sentences we get correct and how many do we make mistakes at. So what we're going to do is take the sentence sushi is great and feed it through the classifier, through the learn classifier. But we don't want the learn classifier to actually see the true label. We want to see if it gets the true label right. So we're going to hide that true label. So the sentence gets fed to the learn classifier while the true label is hidden. And now given the sentence, we're going to predict y hat as being positive. So we believe this is a positive sentence, and so we've made a correct prediction. So the number of correct sentences goes up by 1. Now let's take another sentence, another test example. So let's say you say, the food was okay as a negative sentence. So that's a bit of an ambiguous sentence, but it's been labeled as negative in the training set. So now I feed the sentence to the classifier, I hide the label, and let's see what the classifier does. In this case, because the food was okay, it can be billed as positive, maybe it makes a prediction that this is a positive sentence. I've made a mistake because the true label is negative. So we say, hey, mistake was made. We now have one more mistake. So we have one correct classification and one mistake. Now we do this for every sentence in the corpus. There are two common measures of quality in classification. So for example, one of them is the notion of error. So error measures the fraction of the test examples that we make mistakes on. So what we just do is say, out of all of the sentences that are classified, how many mistakes did I made? So number of mistakes. And I divide that by the total number of test sentences. So for example, if there were 100 test sentences and I made 10 mistakes, then our error will be 0.1 or 10%. Now, the best possible error that I can make is 0, basically. I make no mistakes. Now, it's common to, instead of talk about error, to also talk about accuracy of your classifier. So accuracy is exactly the opposite of that. So in accuracy, instead of measuring the number of errors, we measure the number of correct classifications. So the ratio here is number of corrects divided by total number of sentences. And unlike error, where the best possible value was 0, in terms of accuracy, the best possible value is 1. I got all the sentences right. And in fact, there is a really natural relationship between the two. We know that error is equal to 1 minus accuracy, and vice versa. We've discussed error and accuracy as ways to evaluate a classifier. Now it's very important to understand the accuracies or errors that you're actually getting from your classifier. Really think deeply about whether those are good errors or good levels of accuracy in your situation. So for example, one of the common mistakes you might make is to say, how good is my classification at all? When you build a classifier, the first baseline comparison you should do is against random guessing. So for example, if you have a binary classification problem, like is this sentence of positive or negative sentiment, then just random guessing is going to give you 50% accuracy on average. So you better beat 50%. If you have k classes, so for example, if you have 3 classes, you're going to have a random guessing accuracy of 33%. For 4 classes, it will be 25%. For k classes, it will be 1 over k. So at the very least, you should beat random guessing really well. Because if you don't, then your approach is basically pointless. Now, even beyond beating random guessing, you should really think deeply about whether your classifier, even if it looks really good, is it really meaningfully good? So for example, suppose you have a spam predictor that gets 90% accuracy. Should you go brag about it? Is that awesome? Well, it really depends. So in the case of spam, not so good, because in 2010 data shows that 90% of the emails ever sent were spam. 90% of the emails. So if I just guess that every email is spam, what accuracy do I get? 90%. This is a problem where this is what's called majority class prediction. So I just predict the class that's most common, and it can have amazing performance in cases where there's what's called class imbalance. One class has much more representation than the others. Spam is much more representative than regular good emails. And so you have to be very cautious and really look at whether you have class imbalance when you try to figure out whether your accuracy is good. And of course, this approach also beats random guessing if you know what the majority class is. So you should always be digging into your problem and understanding, really thinking about the predictions you're getting and whether that accuracy is really meaningfully good for your problem. So ask yourself questions like, is there a class imbalance? How do I compare against baseline approaches like random guessing, majority class, and really fancier things than that? And most importantly, think about your application and ask yourself, what is a good enough accuracy to make my users really happy? So if in spam filtering, if your accuracy is not that good, then there will be important messages going to the spam folder, and that could be a really bad thing. We've talked about accuracy and errors that a classifier might make, but there are different kinds of errors. So these kinds of errors are called types of mistakes. It's important to look at the types of mistakes a classifier might make. And one way to do that is what's called a confusion matrix. So let's dig that in a little bit. So we're talking about the relationship between the true label and whatever classifier predicts, so the predicted label. So let's say that if the true label is positive and we predict a positive value for that sentence, we call that a true positive because we got it right. Similarly, if the true label is negative and we predict that negative, we call that a true negative. That's good because we got that right. Now there's 2 kinds of mistakes that I can make. So for example, if the true label is positive, but we predict it as negative, we call that a false negative. We said it was negative, but that was false because it was positive. Similarly, if the true label is negative, but we predict it as positive, we call that a false positive. It was negative, but we predict it as positive. And false positives and false negatives can have different impacts on what can happen in practice with your classifier. So let's look at a couple of practical examples of that. So let's look at 2 applications and what the cost has of false positives versus false negatives. So if we consider spam filtering, a false negative is an email that was spam, but it went into my folder, you thought it was not spam. So that's just annoying. I got another spam email in my inbox. Maybe it's bad, but not super bad. However, if you look at a false positive, that's an email that was not spam, that got labeled as spam, went to my spam filter, I never saw it, I lost that email forever. That has a higher cost. Now we can also look at medical diagnosis or other applications as a second application. So what's a false negative in medical diagnosis? False negative is there's a disease that I have, but it didn't get detected. So the classifier said it was negative, I don't have the disease. So in this case, the disease goes untreated, which could be a really bad thing. But the false positives can also be a bad thing. That is, I classify as having the disease where I never had the disease. And in this case, I get treated potentially with a really bad drug with lots of side effects for a disease that I never had. So it's a little bit unclear what's worse, having a false positive or a false negative. In medical applications, it really depends on the cost of the treatment and how many side effects it has versus how bad the disease can be. Now, this relationship between the true label and the predicted label, false positives and false negatives, is called the confusion matrix, this matrix that we just drew. So, for example, let's say that we have a setting with 100 test examples. And we have of those, 60 are positive and 40 are negative. So there's a little bit of class imbalance, but not too much. So of those 60 true positives, if I say I got 50 of them correct, while of the 40 true negatives, I got 35 of them correct. Let's see what we've learned. So out of the 100 examples, I got 85 correct. So we can talk about accuracy. Accuracy is 85 correct over 100, which is 0.85. And we can also discuss the true positives and the true negatives. Sorry, the false positives and the false negatives. So of the positives, I got labeled as negative. That's a false negative. And that was 10. I had 10 false negatives. And on the other hand, of the true negatives, we get 5 false positives. So in this example, we got 85% accuracy. We got a higher false negative rate than we had a false positive rate. Now, those words, false positive, false negative, apply only for binary classification for 2 classes, but the ideal confusion matrix works well even when you have more classes. So let's talk about a simple example of that. So let's say that I have 100 test examples, and this is for medical diagnosis. So there's 3 classes, healthy, cold, or flu. And of the 100 test subjects, we had 70 with they were healthy, 20 that had cold, and 10 that had the flu. And let's suppose that we got 60 correct for healthy. We got 12 correct for cold, and we got 6, 12, 8 correct for flu. So at the total, our accuracy here was 80, which is 60 plus 12 plus 8 divided by 100. So that's 0.8, 80% accuracy. But we can talk about the false positives, the false predictions. So from healthy, there were 10 mistakes. And we can say it's more common to confuse healthy with having a cold than it is with having the flu, because the flu is a more complex disease. So we might have those 10 mistakes, 8 were confused with cold and 2 were confused with flu. Cold can go both ways. So we made 8 mistakes. Maybe you can say half of them got confused with healthy and half of them got diagnosed with something stronger, the flu. While of the 2 mistakes for the flu, then maybe you would say that we made no mistakes as healthy. Nobody that came in with a flu was thought, oh, you're healthy. But 2 of those 10 were thought to have just a cold and not the flu. So this is an example of a confusion matrix. We can really understand the types of mistakes being made, and we can interpret those. And this is a really important thing to do in classification. In the regression module, we talked about the relationship between error or accuracy and the complexity of the model. Let's talk a little bit about the relationship in terms of the amount of data you have to learn, and really explore the question of how much data do we need to learn. And this is a really difficult and complex question in machine learning. So Of course, the more data you have, the better, as long as the quality of the data is good. Having bad data, lots of bad data, is much worse than having much less, much fewer data points, but really good, clean, high quality data points. Now, there's some theoretical techniques to analyze how much data you need. Many of those help you understand kind of the overall trends, but really tend to be too loose to use in practice. In practice, there's some empirical techniques to really try to understand how much error we're making and what that kind of error looks like. And in the follow-up courses, we're going to explore those techniques much further, but let me give you a little bit of guidance and a little insight on what I can do within the classification setting. Now, an important representation for this relationship between data and quality is what's called a learning curve. So a learning curve relates the amount of data that we have for training with the error that we're making. And here we're talking about test error. Now, if you have very little data for training, then your test error is going to be high. But if you have a lot of data for training, your test error is going to be low. And now the curve is going to get better and better as you get more and more and more data. Whoops, didn't go through that point, so I'm going to just erase it. And here we go. This is an example learning curve where the quality is getting better as we add more data. Now you may ask, is there a limit? Is this quality just going to get better and better forever as you add more data? Now we know that the error is going to decrease as we add more data, the test error. However, there's some gap here. And the question is whether that gap can go to zero, and the answer is in general no. This gap is called a bias. So let's discuss a little bit what this bias or this gap is. So intuitively, it says even with infinite data, the test error will not go to zero. So let's understand why a little bit. More complex models tend to have less bias. So if you look at a sentiment analysis classifier that we've been building, if you just use single words like awesome, good, great, terrible, awful, it can do okay. Maybe it do really well, maybe it just does okay. But even if you have infinite data, even with all the data in the world, you're never going to get this sentence right. The sushi was not good. Because you're not looking at pairs of words, you're just looking at the words good and not individually. And so more complex models that, for example, deal with combinations of words, for example, there's something called the bigram model where you look at pairs of subsequent words like not good. Those models require more parameters because there's more possibilities. They can do better. They might have a parameter for good, say 1.5, but not good, say minus 2.1, and actually get that sentence, the sushi was not good, correctly. So they have less bias. They can represent sentences that couldn't be represented otherwise, but so they're potentially more accurate, but they need more data to learn because there's more parameters. There's not just parameter for good, there's now parameter for not good and all possible combinations of words. And the more parameters your model has, in general, the more data you need to learn. So let's go back to our example. We talked about the effect of amount of training data on the test error. So let's say that I'm building a classifier using single words. And the question is, how does that relate to a classifier based on pairs of words? Now, for a classifier based on bigrams, when you have less data, it's not going to do as well because it has more parameters to fit. But when you have more data, it's going to do better because it's going to be able to capture settings like the sushi was not good. And so the behavior you're going to get is something like this. And at some point there's a crossover where it starts doing better than the classifier with single words. But notice the bigram model still has some bias here. although the bias is smaller, it still has some bias. So far we've talked about classification in terms of just predicting, is this a positive sentence or a negative sentence, is it email spam or not spam, but in general you want to go a little bit beyond that and ask about what is the probability that this email is spam. So how confident am I on the prediction? Instead of just looking at positive and negative, I want to know how sure I am about the prediction. So for example, if you take a sentence like, the sushi and everything else were awesome, that's a definite plus, definitely positive. However, the sushi was good, the service was okay. It's probably a plus, but I'm not so sure, it's not as definite. And so what a classifier will often do is not just output is positive or negative, but output how confident or how sure it is. One way to do that is to talk about probabilities. So here we have to put the probability of being a positive or negative sentence given the input sentence X. So the output label, what's the probability output label given the input sentence? So for example, for the top example there, instead of saying a definite plus, we say the probability that it's a plus given X input sentence is 0.99. While in the second one, the probability of being a plus given X is only 0.55 because I'm kind of uncertain about things. Predicting probabilities or level of confidence is extremely important. And as we'll see in the classification course, it allows you to do many things. So for example, when we know the probability, you can make decisions like what is a good decision boundary that trades off false positives and false negatives and balance between the two. We've now seen how cool deep learning can be. We can apply in a wide range of areas and get really high accuracy by learning really detailed features of our data and how neural networks can support that. We've seen how it can be applied for various tasks in image analysis, in computer vision. Let's now revisit the block diagram that we saw summarizing regression and classification and other machine learning tasks and how it can be applied here for computer vision, for deep learning. So in particular, let's talk about deep features for classifying images. So deep features for image classification. The input here are pairs of images with their labels. So the labels that we've looked at were things like, whether it's a cat, a dog, a house, or some other object in the image. And now we feed that through the feature extractor. And in this case, we're using a deep learning model as a feature extractor. So the output here are what we call the deep features for this particular image, for every image. And now we feed in this images, representative features through a machine learning model, where we use a simple classifier like logistic regression in here. Say logistic regression as an example. And the output is our predicted labels. Predicted labels. And so we're going to feed in our predicted labels y hat and the true labels y into our measure of quality. So y and y hat, and the measure of quality depends on your task. For this task, we use classification accuracy. And so the parameters w hat are really the parameters of the weights of the logistic regressor. So these are our weights on features. And what the machine learning algorithm is going to do is take the classification accuracy, try to make it a little better by changing those weights w hat and updating them. We've now seen how deep learning can give you really cool and exciting results for various tasks in computer vision. And we saw those applied both to classification and to retrieving of new images using raw neural networks as well as deep features. And our notebooks that we explored showed us that it's really easy to build such deep learning models and actually apply to a really cool machine learning task in computer vision, both in classification and image retrieval, which allows me to find exactly the kind of shoes that I'm really excited about. And with this, you'll be able to build a really exciting intelligent application that uses one of the most sought after techniques today in machine learning, deep learning. Emily and I really hope you've enjoyed the course so far. We've really explored the foundations of machine learning on a wide range of domains with a range of different applications and really touched many of the practical issues around deploying and building machine learning systems. And now in this closing module, we're going to really summarize some of the concepts that we learned, talked about how to deploy these ideas, this machine learning systems in production, and then what's ahead in the specialization and in machine learning as a whole. Some really exciting stuff as we close off this first course. Now, so far, we've really just talked about, how do you build a machine learning model using data, how do you measure its quality, and how do you understand whether it's working or not. But that's not enough to build an intelligent application. When you build an intelligent application, you want to take that model that you learn and then really put it in front of, say, the customers of your company who are going to your website to buy a product. So what does that process actually look like? There are many different aspects associated with it. This is what we call model deployment, where we're taking the model and really allow it to serve predictions in real time. And we'll talk more about that. Then we have to talk about how do we evaluate a model to make sure what we did offline as we're training the model is still good in the long run as we're using it. Then we have to think about all the management pieces. How do we make sure the model is still good? How do we replace it when the model improves? And how do we react to measurements that we make, which are actually the metrics that we monitor over time to try to understand whether our models are still good or it's time to relearn them from data. Now, all these pieces are really coming together. They're not just individual, separated ones, but all kind of interacting pieces that we need to understand deeply and create a cycle of improvement of the models that we have. So let's start with the first one. Let's start with the deployment piece. Now consider the following setup. You're building a really cool new kind of product recommender system and you're using a bunch of data with millions of product reviews and users, and you want to take the model that you learned on your laptop or in your desktop or in a big cluster of machines and deploy it on a website that really interacts with your users. What does that look like? Well, that whole system starts with some historical data, some data that you've collected about the users of your system, the reviews they've written, what preferences they have, and we take that data and we feed it to train a model like we saw in the recommender systems module that Emily talked. That process with historical data is usually done in what's called a batch offline setting. You learn a model, say on your desktop machine or in a cluster, and then take that model and deploy it, for example, in the cloud, so that you can do what's called serving predictions. This is the online real-time part of the system. So for example, if you have a website, if this is what we're serving for, the website is going to give me information about my users, what they're doing right now, what pages they looked, what products they're thinking about buying. And then from that, we're going to serve predictions in real time to say, oh, check out this giraffe, chew toy, remember that? Check that out, as this might be something that you want to buy right now. Now, the user sees that giraffe offering, and they may or may not buy that giraffe. So that's the kind of feedback we're going to get back from the system. Did the user buy it or did they not buy it? And that's going to influence both our real-time decisions and go back to our historical data and really be collected in the long run so that we can improve our model as we collect more and more data from the world. So that's what a holistic deployment system for machine learning might look like. Now we've talked about that initial deployment, taking a model that we learned for recommender systems and deploying it as a service that your website can query. But there's more to that deployment process and to machine learning in production. There's that deployment piece, but there's also the management of models, there is the evaluation, and there's monitoring collection of metrics. So let's talk about those last three pieces. And those pieces are really about taking those models that we've learned, seeing how they're performing in practice, not just in the batch offline process, but with real users in practice. And use that information to train new models and deploy new models and update the models as we gather more information about the world. So if we go back to our pipeline, which involved the batch process and the real-time process, now that feedback piece where the user maybe bought the product or didn't buy a product they were recommended, that gets fed back into both the real-time data but also the historical data, is going to be very useful for us. We're going to use that feedback to go back and learn new models. So for example, now that we have more historical data, I might learn a second model, let's call it model 2 for recommenders, which I think is better, and I'm going to start serving that model in production, and I figure out, is this model 2 really better than the old model 1 that I had? Which one is better? How do I figure that out? That's some of the key questions around managing models in production. So when we figure out when to update to model 2, if it's worth it, and how do we choose between models. And this is really about monitoring the models in production with real users and understanding what those usage patterns look like. And the key piece to monitoring models is evaluation of models in production. So this is really combining the predictions that we're making with the metrics. What are users doing in real time with our system? So the questions around here that you need to address when you deploy models are, what is the data they're collecting from users? Not just the data that you had historically, but what data you're collecting from that real-time interactions where the users are buying or not. And what are the metrics they're going to use to measure whether those interactions are good, whether you're getting the right kind of response you're hoping for, whether machine learning is actually working for you in the system that you've built. Now, if we go back to our pipeline, you can imagine saying, okay, I'm going to collect that data and I'm going to use to measure the metrics that we use to train my model. So for example, when we talked about recommender system, we talked about one such metric. We discussed minimizing some squared error. Now, is this the right metric to evaluate in production? It's a good metric to optimize a model offline, but in production, you really care about whether people are buying a product or not, or whether this machine learning model is getting your users more engaged for website, whether that model is helping people use their smartphones better, or their wearable watches, or whatever technology that is using machine learning in the background. So some squared errors or some offline training, those models are really about those metrics are really about optimizing the model offline and figuring out whether a model is good and perhaps whether it can be updated. Now the online metrics, let's say who's buying, the usage metric, how is this changing, the bottom line for my business. This is really about kind of choosing whether the old model is better than this new model I've created. And let's talk a little bit about what the process looks like. So the question here is, should I update my old model with a new one that I learned that will have new data? And there's many questions around this. Why should I update? Why should I take what I've done before and change it with something new? And this has to do with, the trends in the world have changed, new products have come in, users' tastes have changed, a fad like, the chewy giraffe that we talked about, goes out of fashion, nobody else wants it. So we want to change that model, we want to update it. So that's what we have to do to say, okay, this is why we should update it, but when do we update it? When do we say, okay, it's time to take that old model and switch it out and put in some new one? This is about tracking real world statistics. It's not about intuition, it's not about, yeah, this sounds like the right time, or, talking to some person who's not looking at data, maybe some, kind of intuitive business analysis. This is really about data. It's about tracking those metrics that we measure, those statistics, and really coming up with a quantitative quality as to say, things have changed, it's time to update the model, this is what's going to happen when we update the model. And this combines those offline metrics when we use to train the model, but really online metrics that we're capturing. So let's talk about how online metrics get used. One example of how to choose between models using online metrics is what's the idea of A/B testing. Let's say you have two models, model 1 and model 2, and I want to figure out which one is going to be better, which one should I give it to my system. So what I can do is give some of my population, we call them group A, let's say some of the people or people from a certain geographic region, let's say people from the United States get model 1, and then let's say people from a different geographic region, let's say people from Canada get model B, model 2. And so you look at the behavior between the two models, capture some metrics, and let's say that model 1 does better model 1 does worse. It only has 10% click-through rate, so CTR. So that means only 10% of the time people are buying the product. Well, with model 2, it's amazing. 30% of the time people are buying the product. So the CTR's click-through rate is 30%. So what you do after you've done this test is say, okay, I've done a test enough, I collected enough test samples, now I'm going to start serving model 2 instead of model 1. Now, there are many other issues and caveats around the ideas we talked about so far. A/B testing, deciding when it's time to switch a model, how much data you have to collect, what to do, is very tricky and it requires a lot of thought. And we'll talk more about it towards the capstone, but really something that you need to think about quite deeply. Now, also, thinking about what versions of model you have. Model 1 and model 2 is a simplification, and typically you have many data scientists capturing their own models with their own ideas. The question is, how do you keep track of that? How do you know what data was used to train different models? How do you keep track of how they're performing? Which ones are performing well, which ones don't? Is it because of some fluke? Is it because of some real property of the data? How do you monitor these with dashboards? How do you come up with reports, say, okay, this is what's happening, this is what machine learning is doing, what difference it's making? All that can be quite complicated. And so it's very important for you to think about not just how do you use machine learning algorithms, how do you write your own methods, how do you pick your features, but how do you keep track of that and make sure the models are working and providing the value that you want for the system that you've built.
Okay, so in this course, we've talked about lots of different machine learning methods and lots of applications where these types of methods can be very impactful. But of course, there are lots of open challenges that still remain in machine learning. So let's discuss some of them. One is the fact that we often have a choice of which model to use. So for example, when we talked about recommending products, we said we could use a classification model where we take features of the user and the product, pass it through this classifier to say whether yes or no the person will like or not like this product. But then we also talked about using matrix factorization, where we were going to learn features about users and products and use that to recommend products to the users. And then we also talked about featureized matrix factorization, combining these two ideas. But the list often of possible models we can consider for a task is very large. So typically, this leaves the practitioner very perplexed. Which model should I use? And searching over this set of possible choices is still an open challenge in machine learning. Another really important challenge that we're often faced with is how do we represent our data? So for example, when we talked about our document modeling or document retrieval task, we said, well, we could use just raw word counts. Or we also talked about we could normalize the vectors. We could use things like TF-IDF to account for very popular words and to more emphasize the important words in the document. But honestly, there are lots of different variants of TF-IDF. We just provided one example of doing this. You could also think about using bigrams and trigrams, and there are lots and lots of ways we can think about representing the words that appear in a document. That's our data set of interest that we'd like to represent. But that's just for a document. Then maybe we have images. How do we represent an image? We've talked about some ways, we'll talk about others, but there's lots of challenges with that. Then maybe you have data that's really network-based, okay, things like from Facebook. So you can have very complicated data structures, and from very, very different diverse data sets, we want to be able to use the types of methods that we've described. So how we represent our data, of course, is going to have significant impact on the types of inferences that we make on that data. So this is a really, really important problem, and there's no one method for choosing the right representation of your data. One of the other really important and really significant challenges we're faced with in machine learning these days is how to scale up in multiple dimensions. So one aspect of this is the fact that data is getting bigger and bigger. So this is something that's been talked about extensively in the media. So let's just describe a few situations in which we're faced with a growing amount of data. One is the fact that there's just a large number of different platforms out there for social networking, collecting data via crowdsourcing and different things like this, sharing your photos, your videos, and reviewing restaurants, and the list of possible ways in which you can now go online and give data to the world is growing. And the amount of people doing this and providing data is just growing at this huge, huge rate. So we have lots of new data sources available to us. And in addition, the way we think about buying products, we no longer often just go to a store and have some handwritten record of what product was purchased. We now have vendors like Amazon who have these huge online marketplaces and collect data about different products and customers and the purchases being made, and lots of data from different sources like this. And beyond these types of websites, there's also a lot of devices that we can now wear. So there are these wearable devices. I can wear a watch that monitors all the activities I'm doing, how I'm sleeping at night. I can wear glasses that record everything that I'm seeing. I can also talk about the Internet of Things, which is just lots of connected devices and lots of different sources of information communicating with one another. So these are just some of the areas in which we're seeing lots and lots of new data sources. But of course, that's not exhaustive. We can also talk about things like medical records. Again, no longer do you go into your doctor's office and just have them write notes by hand that gets put in some file. Often they're taking electronic health records, and these are now communicating across systems. And we have lots and lots of electronic health records that it's just a source of data to be parsed and understood and used to innovate in medicine. So lots of new data sets, which is exciting. We can learn a lot about how people operate, about our bodies, about how people purchase and make friends, and how they go about their day-to-day activities. But of course, we need to have methods that scale to analyzing these types of data sets, and also to the unique structure of data that's presented in these data sets, and the noisy structure. And the list of challenges is really extensive. So this is one of the very big challenges in machine learning, is how to deal with this big data. And simultaneously to data being really large, we're also faced with a challenge with the fact that the models that we're using to analyze these increasingly complex data sets are also growing. So the models themselves are becoming bigger and more complicated in order to extract information from these ever-growingly, I don't know if that's a word, but you get my point, these very intricate data sources and very large data sources. So just as an example, when we talked about clustering, we talked about this application where you have recordings of brain activity taken over time. So this is just one quick example of a model that was used to analyze this type of data set. And without going into the details of what's shown here on this slide, just realize that there are lots of circles and lots of arrows. And what that means is that this is a really complicated, big model. So you might think, okay, well, data's getting bigger, models are getting bigger, but that's okay because processors are getting faster. Well, that was the story for a while. We were seeing this exponentially increasing rate of increased speed for our processors, but that stopped about a decade ago. And now what we're seeing is really very marginal increase in the speed of an individual processor. So instead, we have to think about new ways to scale up. And the typical thing that we're leveraging these days is collections of processors. And there are different architectures that we have. We have things like GPUs and multi-core and clusters and cloud computing resources and really fancy and expensive supercomputers. So that's great. Those are really powerful or potentially powerful computing resources that we have. But the question is, how do we use these in machine learning? And in machine learning, we have a number of challenges we're faced with. One is the fact that taking our machine learning algorithms and thinking about how to distribute them across these different processors and run everything we want to run in a coherent way is very challenging. Another challenge is, how do we distribute the data across these different machines? And how do we do all of this in a way that's very tolerant to different failures we can have of the individual machines. So these represent a number of challenges that we're facing in machine learning, and a lot of exciting research is coming out to start addressing these problems. Okay, given your great historical perspective on machine learning...
Are you calling me old?
I am calling you old.
It's always like this.
I was wondering if you could give me a little perspective on the future.
Well, let's talk about the present.
Okay. I'll accept that. We can talk about the present. He always makes things really long and really detailed, so just talk about the present. We'll get to the future eventually. Don't worry. Here we go. The present. What is the state of machine learning,
I'm
Carlos?
really excited about machine learning today, honestly. Being old, I've been working machine learning for a long time, but today, every time I open a web app, it uses machine learning inside, and that's pretty cool. And I pull out my phone. Where's my phone? You always have your phone with you.
I actually don't have my phone right now.
She's always on her phone. Anyway, when you pull out your phone, every time you use it, there's a system that uses machine learning right inside, the cloud that supports it, which is really pretty cool. And now with devices, check this out. I got this watch. It's a wearable watch that tracks my activity. Knows when I'm running, when I'm biking.
Knows when he's sleeping or not sleeping. Always this debate. Who got less sleep with the baby?
That's a wearable watch. And underneath these things, it's all using machine learning. So we're seeing the power of machine learning just kind of again and again being used today. But I think we've only scratched the surface of what machine learning can do. Like, where do you see machine learning going in the future? You tell me.
Where do I see it? Well, I know probably a lot of ways in which it would be useful to Carlos. One being the fact that he hates driving. So, of course, there's this smart car idea that this self-driving, not smart car. Ugh.
They're also smart.
Are they smart? They're pretty smart, I guess. It's a self-driving car. A smart car is a brand. That's not what I mean. I don't mean those little cars. I mean normal cars that drive themselves.
That would be really useful for me because I don't like driving. I only like biking. And so, at least
self-driving bikes.
No, I like
that's for when you get really, really old.
So I'm excited about that. But when I think about me getting old, I think about how machine learning can really have impact with the idea of personalized medicine. And the question here is, why is it when I go to a doctor for a certain disease or certain condition, the treatment that Emily gets is exactly the same as the treatment that I get? I mean, we're different people with different lifestyles, with different body types, as you can see, and still with medicine, we're getting exactly the same treatment. That makes no sense. The treatment needs to be personalized to who I am, what I do, how much of a couch potato I am, what my DNA looks like, and with machine learning, we're going to be able to do that all the time. It's really super cool. I'm pretty excited.
Carlos is so optimistic, which is good. It's really nice. But it's hard. It's really, really hard to do this. The data is really noisy because there's some doctor who's there taking these records, making notes about Carlos's health conditions compared to mine. And there's lots of missing data because, maybe Carlos skipped his last checkup, or the doctor forgot to enter something, or maybe the doctor put something under a different entry than they did for me. And so somehow our machine learning algorithms are going to have to be able to parse this really complex and noisy data in order to do this type of personalized medicine, which I think is a possibility. I think it's really cool. But
it is hard. Honestly, all these things that we're talking about, from self-driving cars, which we're seeing as a reality today, through personalized medicine, it's all hard stuff. But, in the future, and this is the optimistic in me, like, the world is going to be personalized to me. Like, you know what I mean? So
the grand goal of everything for Carlos.
for me and for Emily too. She can have her own world. So the idea that today when we go to the web, when we buy things, we have to go through very similar experiences as others, but as the world becomes smarter, as more data is collected, as we come up with these algorithms which are robust to all this kind of noise in the data, we're going to have experiences that are really unique to us, idiosyncratic, and we're not going to suffer as much from technology. Technology is going to really adapt to us, which is really super cool.
I agree. I think that is a really, really exciting goal, and I think that is one of the directions that machine learning is going in. But I think something else that's really cool is even doing the things we can do right now, but doing them as the data is coming in real time with really complicated different types of data sets and putting all this information together. And maybe it's just even still recommending products, something we've done before in the past, but with different types of data. And again, in this really fast, rapid online type of setting, and getting feedback and incorporating this to make these types of predictions.
Yeah. Dealing with temporal data, which is like the topic here, as well as the spatial data, like location data, all these kinds of different data sets, images, video, audio, sensing data, combining all these different data sources in real time is one of the big challenges. And what I'm excited to see is that there's a lot more machine learning work and a lot more algorithms being developed that try to address this kind of fusion of different data types. And that's a really cool topic to work on right now.
For sure.
Now,
so
of course,
we hope that's really exciting to you, in addition to us.
Yeah, no, it's exciting. And of course, the methods that we develop have to scale to these massive data sets that we're talking about, different kinds of data, be able to be really useful and robust as you have noise in the data. And honestly, it shouldn't require a PhD in machine learning to be able to access the systems and be able to use it. So part of the challenge that we have to do is be able to make these algorithms robust and these methods robust so that a wide range of people, even those that don't have the most theoretical background, are able to build the smartest, coolest applications that use machine learning. And that's exciting to me as well.
Absolutely. Okay, so now that you guys are psyched about the future of machine learning, let's talk about what we're going to cover in this specialization. Okay, so in the regression course, now that you guys know what regression is, we're going to go through a lot more of the details on different formulations for models. For example, how to cope with lots of features, something that we alluded to in this course. And we're also going to talk about, in great detail, algorithms for fitting these models. So different optimization algorithms, remembering now that we've seen that there's this cost we can talk about, residual sum of squares and minimizing it. We're going to talk about different optimization algorithms like gradient descent and coordinate descent for actually doing this optimization. And then through this case study in predicting house prices, we're going to cover a lot of concepts that are really foundational to machine learning in many different areas. And some of these include, how do we think about measuring cost? How do we think about choosing between models and dealing with overfitting of our model? So we're going to explore this in this context, but again, these ideas generalize well beyond regression and well beyond predicting house prices. Then when we get to the classification course, we're going to talk about specific examples of linear classifiers. We're also going to talk about methods of how to scale up to using lots and lots of features and creating classifiers in this very high dimensional feature representation. And again, we're going to talk about algorithms for performing these types of classifications, specifically looking at an optimization algorithm that allows us to scale up to really, really large data sets. And we're also going to talk about this idea of how we can think about blending different models using something called boosting. And again, we'll look at many different concepts. And one that I think is really interesting is how to do something called online learning, where we get data that just continually streams in, and we like to make our inferences continually as we get that data. Then when we get to clustering and retrieval, again, we've gone through the foundational ideas of what does it mean to do clustering and what is our document retrieval task, but we're going to step it up even more, where now, for example, when we think about clustering, a document might not just be about sports or world news or science or entertainment. Maybe a document has some mixture of different topics. We can very easily think about a document that's about both finance and world news. And so we're going to think about how we model this more complicated structure that might be present in our data. And for the algorithmic side of things, we're going to look at very efficient ways for searching over data when we're doing our retrieval tasks, and lots of different algorithms for doing the types of clustering models that we're talking about. And in terms of really important concepts that we're going to cover in this course, one thing is thinking about how to scale up doing the clustering to really, really massive collections of documents using something called MapReduce. Next, we're going to turn to our recommender systems and dimensionality reduction course. And here, beyond the types of collaborative filtering and matrix factorization that we already talked about in this course, we're also going to talk about ways to take high-dimensional data sets and think about modeling in terms of some lower dimensional representation. And so for that, we're going to think about different algorithms for doing this dimensionality reduction. And we're also going to talk about algorithms for fitting the types of matrix factorization models that we described in this course. And in this case, some of the important concepts we're going to go through, especially when we're thinking about matrix factorization, is how we think about doing something like matrix completion. And that's where we're filling in all the unknown squares, if you remember that from this course. And then a more general problem, which is this cold start problem, where we, in the case of our recommender systems, might have no information about a user or a product and want to form those recommendations. And finally, we're going to get to the capstone, which is really, as I hope you guys have gotten a sense, going to be very, very cool. And now that you've gone through this course, you understand some of the concepts that we talked about in terms of what makes up this capstone. In particular, we're going to look at a recommender system that combines ideas of doing text sentiment analysis with important ideas from computer vision in terms of searching over different images. And for doing this, we're going to use deep learning. So there are going to be some really important and more detailed information about deep learning presented in the capstone. So please get to that point. It's really going to be cool and very important. And all of this is going to allow you to build this really intelligent web application and deploy it and do things that impress not just your friends and family, but also potential employers. So of course, that's a potential bonus to some of you out there. But it's really going to be a lot of fun. So we hope you get to that point and enjoy the capstone project. So we hope you've enjoyed this first course in this machine learning specialization. And not only have you learned a lot of different machine learning methods, but you've actually put them into practice.
And we really appreciate your effort. We know you've worked really hard, you've implemented a lot of different machine learning algorithms and really gone through those notebooks and really understood not just kind of the concepts, but how to put them into practice and really how to evaluate whether those models that you built really work and provide the value that you expect out of machine learning. Now you're ready to build your own intelligent applications and really deploy them in practice.
But there's a lot more ahead for us in this specialization to turn you guys into machine learning experts where you can actually design and deploy new methods. Was there more I was supposed to say? Of course.
That's exciting. Or am I saying exciting?
Oh, let's both be excited. We're all excited. We're both excited for this journey that you have ahead with us in this specialization. It'll be very meaningful.
It's really cool to have you join us. Thank you for coming to the first course. We're excited to see you over the following courses and see the amazing things you're going to build in the capstone project at the end. So there. Okay. Thank you for your hard work.
Thank you. See you soon.